Hello, everybody. In Module 3, I discuss models of agency problems. Module 3 has 6 lessons. Today, we're focused on Lesson 2. I'm going to use simple models to illustrate insights of basic moral hazard models. In the previous lesson, we discussed the general insights of moral hazard models from a big picture perspective. In this lesson, we're going to illustrate those insights using a binary effort, binary outcome framework. It means effort can be high or low, and outcome can be high or low. For more rigorous treatments in more general settings, check Holmstrom 1979, Bell Journal of Economics. Let's look at the model. There is an agent. The agent exerts effort A that is not observed. A determines the distribution of an outcome X that is observable to the principal. As mentioned, A is binary, it can be either AH or AL, and X is binary, it can be either XH or XL. The probability of X being XH conditional AH is PH. The probability of XH being AL is PL. We assume that pH is bigger than PL, which is an intuitive assumption that higher effort is more likely to generate higher outcome. Exerting effort is costly, so we normalize the cost of exerting AL to be 0, and the cost of exerting AH to be V. The principal chooses how much to pay the agents when the outcome is XH, denoted as SH, and how much to pay the agents when the outcome is XL, denoted as SL. So the principal chooses SH and SL to maximize the principal's expected payoff, because the principal is risk neutral, so it is the expected outcome of the project minus expected payment to the agents, subject to the 2 constraints. The first constraint is the individual rationality constraint, or IR constraint. It means that the agent's expected utility for exerting high effort has to be at least as high as the agent's reservation utility, U lower bar, which can be interpreted as the agent's outside option. The second constraint, the incentive compatibility constraint, means that you have to make your contract incentive compatible for the agent to exert high effort, because you cannot observe effort. If you look at the left-hand side of IR and IC, they are the same. They represent the expected utility of the agents conditional on exerting high efforts. The right-hand side of the IC constraint represents the expected utility of agents when the agent is exerting low efforts. So you can see here, on the right-hand side, there is no minus V, because the cost of exerting low effort is normalized to 0. And also, the probability that the agent is getting paid SH and SL is different, because the agent is exerting low effort in this case. So how to solve for those models? For those contracting problems, first step is to identify which constraints bind and which constraints do not. So as we see in the previous slides, those constraints are greater than or equal to. When bind, it means that the constraints holds with equality. When it does not bind, it means it holds with strict inequality. Why do we do this? Because by doing this, you can significantly simplify the problem. And sometimes, as in this case, you don't need to solve the maximization problem. You can directly get the solution. For this problem, we can show that both IR and IC constraints bind. Why is that? What is IR? IR means expected utility of the agent conditional exerting high efforts is bigger than the reservation utility. If IR is not binding, it means you're paying the agent too much. You're paying them higher than the reservation utility. So you are leaving money on the table. You can reduce the payment to the agents, increase the payoff for the principal, while still making the agents earning better than the expected outside option. What is the intuition for IC binding? IC binding means that you're imposing too much risk on the agent's contract. USH is much too larger than USL. Of course, in this case, it is incentive compatible, because when the agent exerts high effort, the agent is more likely to get paid SH than SL. But you're imposing too much risk by not binding IC. So you can reduce USH a little bit and increase USL a little bit, while still satisfying the agent's IC constraint. But in this case, because you reduce the risk in the compensation contract, and the agent is risk averse, so you can reduce the risk premium paid to the agent. You can reduce the expected wage payment to the agent, and that will be beneficial to the principal. So we have 2 binding constraints and 2 unknowns. We can directly solve them, and this is the contract. Now compare this contract, which is what we call the second best case, with the first best. The first best is when you can ignore IC because you can directly observe A. And so you can impose a sufficiently large penalty if the agent chooses low effort. So you don't need to make an incentive compatible for the agent to exert high effort because you can directly observe the effort. In this case, if you don't consider IC, then the first best contract means that you get a flat, the agent gets a flex the wage contract at U lower bar. And the reason is because the agent is risk averse. So the cheapest way to pay the risk averse agent is to give the agent a fixed wage, reduce the risk premium to 0. And so you can see compared with the first best, the second best, the optimum contract under moral hazards, put some risk on the agent's payment. And this is intuitive because if you put USH is bigger than USL, you can induce the agent to exert high efforts. Because exerting high efforts, the agent is more likely to be paid SH versus SL. And you can also see here, the larger PH minus PL is the smaller the spread between USH and the USL. Because the larger PH minus PL is, the more informative the output X is about efforts. And therefore, you don't need such a bigger spread. So this is the risk-averse agent setting. We now discuss an alternative formulation. Risk-neutral agents with limited liability. So now we assume that agent is risk-neutral with one more characteristic. The agent has limited liability, means that the payoff to the agent has to be not smaller than some lower bound. And risk neutrality with limited liability, that actually not very different from risk aversion. It can be seen as an extreme version of risk aversion. Limited liability means that the agent's payment cannot go smaller than some lower bound. That just means the agent is infinitely risk averse when the downside exceeds that lower bound. However, the benefit of using this formulation is the algebra is much simpler. It's much more tractable. So you can use this framework to incorporate other interesting features. This is pretty similar to the discrete Kyle type model we discussed in module 1. It is very simple. It preserves the key intuition of the Kyle model. So it can be used to incorporate other issues, such as the feedback effect we see in module 2. Now let's look at the setup of the risk-neutral model. Again, binary effort, binary outcome. PH is bigger than PL. Higher effort is more likely to generate higher outcome. Again, the cost of exerting low effort is normalized to 0. The cost of exerting high effort is V. The principle is risk-neutral. So the principle's utility function is outcome minus the payment to the agent, X minus SX. And the agent's utility function is SX, risk-neutral. But of course, the agent has a limited liability constraint, which requires that SX, the payment, has to be bigger than or equal to 0 for any X. The principle chooses SH and SL, the payment to the agent when the outcome is XH and the outcome is XL respectively, to maximize the principal's payoff function. The principal is risk-neutral. So your payoff function is the same as the risk-averse case. Now, subject to 3 constraints. In addition to the usual IR and IC constraints, the limited liability constraint here means that the agent payment has to be bounded below some lower bound. And without loss of generality, we set that to 0. So the key difference between the risk-neutral model and the risk-averse model is that in the risk-averse model, IR always bind. We already talked about the intuition, you don't leave money on the table. But in a risk-neutral model, IR may not necessarily bind. Intuition for IR binding the risk-averse model is you can always reduce the payments such that the agent still gets better than the reservation utility, but it increases the payoff of the principal. But in a limited liability case, it may not work because you cannot reduce your payments below some lower bound. First, suppose the reservation utility is sufficiently large. In this case, the limited liability is not going to bind. Because the reservation utility is sufficiently large, you got to pay the agents positive amounts, regardless of the outcome. So in this case, both SH and SL will be strictly bigger than 0. that means your limited liability constraints does not bind. And in this case, the moral hazards does not cause any issue. Of course, you have spread in your contract because SH is bigger than SL in order to induce high efforts. However, the spread does not cause any distortion because the agent is risk neutral. So there is no risk sharing issues, even though there is spread. The agent does not care about it. So we now focus on the more interesting case when the reservation utility is not sufficiently large. So in this case, the limited liability constraints can become binding. So the IC constraint is equivalent to SH minus SL bigger than some number. The intuition is the same as in the risk-averse case. You need spread on payments to the agent to induce the agent to exert high efforts. So the principal's payoff is clearly decreasing in SH and SL, which means if you want to maximize the principal's payoff, you want to set SH and SL as small as possible. So if your reservation utility is smaller than this number, the principal is going to set SL equals 0 and SH equals V over PH minus PL. In this case, IC constraint is satisfied. And SH and SL is at its lowest possible level without violating the limited liability constraint. Principal may want to set SL even lower, but the principal cannot do it because the limited liability constraint now binds. And when your reservation utility is smaller than PH times V over PH minus PL, clearly the IR constraint is not binding because the agent's expected utility is PH SH plus PL S plus 1 minus PH SL, I'm sorry. So in this case, it's going to be PHV over PH minus PL, and that's going to be bigger than the reservation utility. In this case, the moral hazard friction results in worse outcome for the principal. In the absence of moral hazards, the principal can just pay a risk-free contract, giving the agent reservation utility. So in that case, the principal only paid the agent reservation utility. So now in this case, the agent paid more. The agent is going to be worse off. So in this case, because the agent is risk neutral, the principal becomes worse off not because of suboptimal risk sharing. It's because of the agent has to be paid more by the principal. The Holmstrom-Tirole 1998 JPE paper, they used this risk neutral framework to show that moral hazards results in inefficiency in terms of you have less positive NPV project being financed. Because in the first best case, all the positive NPV projects should be financed. But with moral hazards, not all positive NPV projects would be financed. This is also called as credit rationing. We're going to discuss this in lesson 6 of this module. However, we're going to discuss that in an adverse selection setting. To conclude, the optimal contracts in a single risk neutral principal and single risk averse agent setting, it always incorporates some risk in a contract, some spread in a contract, in order to provide incentives for the agent to work hard. Risk neutral agent with limited liability that provides an alternative and, in some cases, much simpler way to study moral hazard problems. And so you can incorporate other features. But the economic insight is essentially the same. The second best is worse than the first best. In the next lesson, we're going to discuss whether we should incorporate information in compensation in the contract to the agent. And if we include, what type of information we should include. If you want to test the understanding of this lesson, a review quiz of this lesson can be found at the link in the slides. Thank you very much.